So this is a reprise of a talk I gave when I was almost when I had first joined Science Circle, just a few months afterwards, and it is the part two of my really it's advice for science fiction writers of how to approach silicon-based life. Um, so I am using the old style. Um, um, what's it called? The old style presenter here, and part two. So part one, I'll kind of reprise part one just basically very quickly. I had really talked about silicon oxygen, like silicates, as a basis for silicon-based life. So that would be maybe high pressure, high temperature, um, and basic, like alkaline conditions. So something that you might encounter deep underground. So really, really like a Horta from the Star Trek universe, exactly. Um, I'm not convinced that Hortas don't exist, but I wouldn't say that in public, or would I? So let's actually kind of talk about life a little bit, right? What is life, and where can I get one? Well, NASA's definition of life is that it's a self-sustaining chemical system capable of Darwinian evolution. And the carbon-based life that you and I are familiar with and are in fact made of, presumably, is a lovely example of that, in that it's a self-catalyzed reaction where the reactants create more of themselves and optimize the process of making more of themselves. So if other chemistry can get started, even in an inefficient way of doing the same sort of thing, that has a chance of leading to life. Yeah, so let's see, that's the left one was Sin, and the one in the back was Tori. They passed away. The one on the right is Seth, and he's about 10 or 11 years old now, so that's when he was a kid. Oops. So, again, why silicon? Well, silicon lives in the periodic table. It is underneath carbon, and the thing about columns in the periodic table is that the columns are arranged in terms of similar chemistry, right? So if we have a column over here, hopefully you can see my pointer moving around. I'm looking at lithium, sodium, potassium, rubidium, cesium. Their chemistry is so very similar. If you have the metals and throw them in water, you've got an explosion happening. Fluorine, chlorine, bromine, iodine, very, very similar chemistry. F2, of course, is much, much more aggressive than Cl2, which is about the same as Br2, and I2 is much less aggressive, but they all have the same sort of chemistry, same things. So it's logical to think, well, maybe silicon can get into some of this action that carbon has. They both can form 4 bonds at once, and when you look at them from an electronic point of view, they are superficially similar. Okay? And in fact, on Earth, silicon can be handled by terrestrial organisms. We know diatoms, they build skeletons out of silicates, basically glass, right? So there are organisms that actually use silicates for structural purposes. Diatoms are photosynthesizing little critters that basically float around in the ocean, have a skeleton. But even bacteria that don't really have anything going for them in terms of wanting to use silicon, um, the Arnold group here showed that just 3 generations was 3 generations of breeding in the presence of SiH4, that's silane. These bacteria decided, hey, this is actually a good source of energy. Um, because the silicon hydrogen bond is very weak, the silicon oxygen bond and the hydrogen oxygen bond are very strong. By breaking up silicon hydrogen bonds and making water and glass, silicon dioxide or silicates, you can release a lot of energy. Um, and it wasn't hard to convince these bacteria to evolve to use that energy if the silane was present. Problem is, silane's a lovely gas. It catches fire on exposure to air, so you're not really going to find it much on Earth. Um, yeah, so um, there's nothing intrinsically stopping silicon from playing a larger role on Earth. It's just its availability is not around. Okay, so yeah, so this is basically the same sort of thing. And I raised the point here. If you had deep sea vents, like say in your science fiction story, there were deep sea vents that were constantly leaking silanes, and that's the simplest one is the SiH4, silicon with 4 hydrogens. It's the silicon equivalent of methane. Um, if there were deep sea vents leaking that stuff, then yeah, there would be a life. There would be life that would most likely colonize those events and use that as an energy source. Probably get some very interesting glass shells around those deep sea vents, right? But that would be essentially carbon-based life forms that we are familiar with, just feeding on these silicates, not really being incorporated as into the chemistry of the replication. Right? So this is part 2. We did part 1 a couple of weeks ago, and the original part 1 I think is still up on YouTube. And as I said, today I want to talk a little more about low temperature stuff, and make sure I do my acknowledgments as well. So, what can you do at low temperatures? So, honestly, at high temperatures, I'm thinking high temperature, high pressure. Water can exist as a liquid under those conditions, but water and oxygen don't let your silanes really persist. So if you want silanes to persist, maybe some low temperatures, some quote-unquote drier conditions, using a different solvent, maybe ammonia as a solvent, NH4. So, let's figure out what a silicon-based life would need to be able to mimic some carbon-based life. So over here, I'm talking about weak, easily disrupted bonds so that structural changes can happen. In DNA, we have adenine, thymine, cytosine, and guanine. And these are our bases, and these bases form the rungs of the DNA ladder. And the T, the thymine, and the A, those match with each other to form what we call hydrogen bonds. And really that's just a region of plus charge and minus charge that attract each other. It's about, each hydrogen bond here is about 1/10 the strength of a carbon-carbon bond, which is a fairly strong bond. So that hydrogen bond, one of them is not particularly strong, but when you add up as many as we find holding the rungs together in DNA, that is a significant force. It means, though, that small sections of DNA can come apart or can be forced to come apart quite easily and can come back together, right? Um, so yeah, one of the points of this slide is that if you look at DNA, you've got hydrogen, oxygen, phosphorus, and nitrogen in there, and in the rest of biochemistry, you've got um, lots of other elements: sulfur, iron, zinc, magnesium, other alkali, and alkaline earth, and all sorts of trace elements, right? Um, could ask, let's see, for DNA, there's phosphorus in DNA. The sides of the ladder are basically held together by POP type bonds. It's like a phosphorus oxygen polymer sort of thing. There was no reason why silicon couldn't do that, but on Earth you can't do it because of the bioavailability. Silicate is just not as available as phosphorus is for this purpose. And I showed you last time the Courbet diagram that would support that. I think I have that. As a later slide. So my advice: use ammonia as a solvent. We won't go into Bard's work in ammonia. I just find it fascinating. But ammonia as a solvent allows you to um, deal with structures that are highly reduced, basically ones that are very electron rich. Ammonia also allows you to create very, very basic, and I mean that in terms of pH, the highly, alkaline species. And that environment tends to allow these silanes to be much more stable. So starting with like ammonia as a solvent, that might be a premise that science fiction writers could use to legit propose some silicon-based life. So here's a Courbet diagram. It's basically something you come across in your physical chemistry classes if you're a chemistry major. And this is called the Courbet diagram for nitrogen. On the x-axis, we have pH. In water, 7 is neutral pH. For ammonia, that's not necessarily the case. For neutral pH, you're basically figuring out what the concentration of hydrogen ions is from the reaction of the solvent with itself. For water, that ends up being at 7. For ammonia, I think it ends up being 11. It's or 12 or something like that. It's much less. So the x-axis has to do with the availability of H+. The y-axis is voltage. It's basically the availability of electrons. And so when you think about the environments, if you have an electron poor environment at high pHs, you get ammonium, right? That would be something you'd find like in ammonium nitrate, a fertilizer. In fact, nitrate, NO3 minus is actually up here. Tend to find it when under more oxidizing conditions. That's what the positive voltages mean here. And at higher pHs, and kind of in the middle, there's a N2. Where you get ammonia is reducing environments, so highly available electrons, and basic, so keeping away H+. Yeah, so this is a lovely diagram. I like Courbet. It summarizes lots of information. Ammonia is a lovely solvent. If you do some, if you look up some videos on ammonia as a solvent, Nile Red actually has a lovely video where he puts some lithium in ammonia that he has generated himself. In this picture, this is sodium, and sodium will dissolve in ammonia. And what it does, you can see the blue color, those are solvated electrons, essentially an electron that is forming a cluster with a group of ammonia molecules. So the blue solutions that you get with these are very, very reducing. They, you know, permit just electrons to go cleanly onto other molecules. After a while, you get, and if you got too much sodium, you actually get this bronze phase, which kind of is like a metallic liquid. I don't know if it's electrically conductive or not, but it is highly reactive. If you shot water at it, you'd have a big problem. There would be an explosion. So yeah, ammonia is just intrinsically more basic, so it's just harder to remove H plus from it. So it's a better environment for complicated silicon chemistry than water. Let's see. Yeah, so some silicon chemistry and older pictures of my cats. So you can make some interesting structural materials from silicon chemistry. So for example, a silicon with 4 alkoxides, right? So think if the R group here is ethyl, so that's a CH2CH3, then silicon O CH2CH3 repeated 4 times would be what this chemical is. It actually polymerizes. If you throw in some water, you can catalyze this with a little bit of acid or base. Either works. It's kind of weird. You can polymerize that to make a glass. It forms a gel phase. It's got a lot of solvent in it. What would be wonderful is if we could remove that solvent easily. You can't remove it easily. You have to go through a lot of effort for it. If you just let it dry, what happens is that the gel collapses, just like when you let Jello dry out. And the problem is that all the little pores that are left behind when the water goes away just collapse, and usually the structure just falls into dust. But if you're careful, you can get a small dense object, or if you use supercritical fluid. So let's say you take your gel that you've made and put it in a pressurized chamber with like carbon dioxide or something, really high pressure, get it to the supercritical stage. Then you can start swapping out the water molecules for carbon dioxide. Carbon dioxide will dissolve the water molecules. And then you really slowly vent the pressure. That'll take away the water and the excess carbon dioxide. If you go slow enough, you retain the size and shape of the gel, but its mass just goes down. The aerogels are extremely light, highly insulating. I mean, if you have a plate of this stuff that's about half a centimeter thick and you hold it in your hand, you can hold a blowtorch on the other side for quite a long time, and it takes a long time before your hand actually starts to feel the warmth. Right, so there's all sorts of lovely things here. So yeah, so basically they have a lot of uses. NASA has used these aerogels to catch micrometeorites. Here's some structures. Basically, the starting material reacts with catalyzed by H plus, really, but starting material reacts with itself to take OH groups or OR groups and make SiO-Si linkages, and eventually you build up larger structures. And in this case, I'm showing you quartz. Okay. So yeah, the organic chemistry of silicon is quite extensive. Here's a example of a molecule. I think I've got that one over here. Let's see if I can move it without deleting anything else in the scene. Yeah. This is a 3D structure. It's a crystal structure. Um, so I keep moving myself here. So yeah, that's a 3D structure, crystal structure of the we get out. That I think lets everyone see it of this material, and this is basically the tan atoms are silicon. The red atoms are oxygen. You can see the silicon oxygen. That's that's basically a silicone, as they're called. So, like, if you have your silicone sealer for plumbing for your bathtub or something like that, that it's basically longer versions of these. Yes. So, all right, let me move that out of the way. My structures that I'm showing you are based on X-ray crystallographic studies. So they are based on actual measurements. Um, the distances and angles come from measurements and not really me being artistic or anything like that. Okay, and here's one where we have silicon nitrogen bonds, and I've got that one up here. Again, another crystal structure. And what we can see is that this particular molecule forms a cage. No reason why it has to form a cage, but this particular one that these guys made forms a cage. And I just moved that kind of up high in front of the screen. Maybe I'll move it a little more. There we go. Yeah, and you can kind of see that silicon can give us some fairly complicated organic type chemistry. Silicon nitrogen bond is very strong. It's less strong than silicon oxygen bond. So, like in water, this would have a tendency to decay um, into probably nitrates and silicates. So, yeah, let's move this out of the way again. Edit. Yeah. Okay. And yeah, I don't think I don't think I've res this one. Again, this by the way is one of those cross-eyed stereograms, and what we can see here is an interesting feature. We've got 3 silicon atoms actually attached to each other, and then we've got all of these. The gray is carbon, the white is hydrogen. We've got all of these methyl groups, they're called. And the reason why we can get crystal structures of something like this, why it's stable enough to form crystals, is that all of the carbon groups shield the silicon from reaction. The silicon-silicon bond is very prone to being cleaved by water, by just about anything. In fact, carbon is going to form long chains. Polyethylene is basically chains of carbon, 100,000 carbons long, right? With other bonds being filled up with hydrogens. Silicon just doesn't like silicon that much. You can't. I think you might get 8 or 9 silicons in a row. You certainly are not going to get 100,000. It's not going to do the same thing. And there are reasons for that. And I talked about that last time a little bit in terms of um, what single bonds, double bonds, and triple bonds are possible for silicon, right? So here's one with it's called a silene, and it's got a silicon-silicon double bond, and all of this organic shrubbery, all of this cabbage that's around that, those two silicons, essentially protect those silicons from the environment so the molecule can, like, exist. Um, so there's reasons for the differences in chemistry, um, and the primary reason is that if you look at the internal structure of where the electrons can go, for carbons, you've got no extra complications. The places where electrons can go onto carbon atoms, when you bring them real close together, they just overlap and there's no repulsive forces happening. Because on silicon, we have these internal lobes um, of where the electron density can go. It's a difference of phase. When you get these silicon atoms too close to each other, the internal structures can start overlapping, and that is actually causing a repulsive force. So it turns out that silicon, if you get the silicons too close to each other, there's repulsion. So double bonds, triple bonds between silicon atoms just don't work. The tag those are not the second shell p orbitals. Um, think of the 3p orbitals as having the same general shape as 2p, but there are internal nodal surfaces. Think of it as a harmonic frequency, and those harmonic frequencies give you a more complicated shape that ends up being represented here as the internal structure. Right. So yeah. So basically, if we're thinking about DNA, all of these A's, T's, C's, and G's, you're not going to have silicon-silicon double bonds like you have the carbon-carbon double bonds and the carbon-nitrogen double bonds. That's a limitation of silicon that takes takes it out of being able to just be dropped in for carbon in our DNA-based life. Okay. Here's another metallosilene, another double bond, and in fact this one is stabilized by interaction with, I bet that's an iron, and this iron has 4 carbon monoxides attached to it. Basically, the silicon-silicon double bond has an iron glommed onto the side of it, kind of stabilizing it. Essentially, it's making the silicon-silicon think it's got a single bond. Really, I throw that in for vanity because this is the type of chemistry I particularly like. Notice how there's 4 silicons bonded to each other in this structure. To get more and more silicons bonded to each other, you have to play more and more of these weird tricks with metal atoms and things. There we go. And finally, I think I have a silyl cation here. We have the green, the thing that looks like a beholder with the green balls, that's a carborine. So that's boron and that's boron and hydrogen. Actually, those green atoms are chlorine, so that should be CB11 Cl 11H. But in any event, that is stabilizing the structure. And let me move it down. And it's just one of my favorite structures to look at, because it's got this lovely ball that stabilizes the silicon, and it actually is a silicon plus. So that would allow some more chemistry to happen there. All right, let me move that out of the way. Edit. Back up we go. All right, and yeah, so there's that, and 3D versions of this, and you know, if you want these, I'll be happy to give. Okay, okay. Let's see. I think do I have a bit of echo? Hey, go Val. I think you've got your mic. Thank you, awesome. Um, so yeah, so basically, let's move on past some of this odd chemistry and into like what the happens on um, gas giant planets. I did want to actually talk about this point just a little bit. There's just like hydrogen bonding holds DNA together, there are other options for bonding. For example, a silicon chlorine bond, um, or a silicon that's got chlorines on it is actually kind of positively charged. And when you have C double bond O's or other organic molecules that are negatively charged, you can make detectable interactions. And essentially what these spectra are showing, the lumps in the spectra are showing the vibrational frequencies. So when you add mass to a spring, it's going to vibrate slower. So up here you have the, in green, you have the rate at which the C double bond O is going to vibrate. When you introduce the other molecule, that spreads out, but you get another peak down here, and that's indicating these other interactions. Right, so there are non-hydrogen bonding intermolecular interactions that could hold a quasi-DNA together, or silicon-based DNA together. So my advice here, if we're going to do cryogenic life that's based on silicon, we're going to have something like liquid ammonia oceans or something like that, and molecules that can be held together by weak intermolecular interactions like the ones I just showed you. Keep the environment cold so that we have ammonia as a liquid. Keep it reducing, very easily available electron density, so maybe lots of hydrogen around, or H2, that kind of thing, to enable silanes to be around. So as silicon fluoride have strong bonds, that would allow us to have these intermolecular interactions. And carbon-based life is so much easier to justify, even under these conditions. So you gotta have some mechanism in your sci-fi landscape that's just taking the carbon away. Yeah, Titan. Saturn itself. And here's another gratuitous cat slide. Here's me with Marduk. And that was a little while ago, and that is my basement. And in fact, I'm sitting right there, not wearing that shirt, but basically that's where I give my Second Life talks from. All right, enough of me. So silicon-based life in the solar system. There was in 2015, 2016. I love the literature. You can find articles and rebuttals. Silicon-based life in the solar system. And the rebuttal, there is no silicon-based life in the solar system. And you know what? They could both be right. One is more hypothetical, and one is realistic. So silicon life on Titan, Neptune, yeah. Tag, neon oceans would be lovely. Neon would be neon. I believe its boiling point's around 20 Kelvin or so. Um, it it is actually interesting as a coolant potentially because neon is in the atmosphere and doesn't really get lost from the atmosphere like helium does. Um, so, and you know, there's a lot of current superconductors that are using the 4 Kelvin helium to be superconducting, but their transition temperatures are such that neon could also work. So that is actually a very interesting idea. The problem with neon is that since it's so inert, it doesn't interact, and making things soluble is harder. Now, liquid xenon oceans, though, that would be cool. All right, so a Neptuna fish. Well, probably not in our solar system, but you know, maybe we can um, think of what it would take for gas giants to have some have some interesting chemistry. So here's a phase diagram, and on the um, y-axis, it's pressure. On the x-axis, I have temperature, and you can see, let's see, this is a water, and so the solid phases of water are fascinating, and I actually, I'll just walk over to them rather than moving them. Oh. So I actually have some of the solid phases of water here. This is the thing I'm like standing in is ice 7. It's a very high pressure form of ice. Basically, looks like body-centered cubic to me. If we're thinking about how that is. So it's not the usual structure of ice. Um, Here's ice 2, and I'm kind of showing you, I kind of got these planes in there. I like them, but they were accidental because I was just learning how to do this at the time. Ice 2 is a very different structure than the regular ice that we're used to. In any event, liquids are very interesting in terms of being able to support life. Well, see what I got for next slide here. I think I've got something on ammonia. Okay. Yeah. So okay. So a small departure here. Um, as you let's say you're on an ice moon. As you go from the surface, which would be the lower left-hand corner of my big red arrow, as you go from the surface down, you would expect the temperature to go up and the pressure to go up. And hey, you might hit a phase boundary. So you might have a shell of ice with a liquid ocean, and at the bottom of that liquid ocean, you'd have another form of ice, the ice 7, in fact. That that would be kind of sad because having an ocean that's just kind of not got rock or interesting sources of minerals and stuff at the bottom of it would probably be very hard to start and keep life going in them. But I bet we're going to find things like this at some point. And you know, again, it's been proposed that maybe there's another fluid phase under more ice, and then we have these onion moons. So yeah, ice 1H is the regular form of ice you and I find falling from the sky or in our freezers. Then these other structures are high pressure. And ice 3, ionic solid, that's really quite a different form of ice. Sodium chloride, table salt, that's an ionic solid. It's basically got uh, particles that are positively charged, particles that are negatively charged, stacked together. And under high enough pressures and temperatures, ice will do the same thing. Right? Ice 7 is very common. That would be at the bottom of these onion moons that I was talking about. So here's a phase diagram for water. And this dotted line here is kind of like conditions on Neptune. And we've actually got some conditions here in the atmosphere where you could have molecular water as a liquid. And then we have these other phases as well, the supraionic phases and the other phases, which are kind of interesting. There we go. Blah, 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 blah. Oh. Yeah, for some reason I had that slide twice. And here's another calculation of phase diagram for water. And again, we have these lines, the white line and the black line, representing what can happen in some gas giants in the atmosphere. Right. So what happens under pressure is that David Bowie and Queen have collaborations. Okay, so gas giants. If you basically look at, we'll ignore the magnetic fields, but if we look at the various pressures that exist on Uranus and Neptune, there's areas of the atmosphere where ionic water, and here I'm calling atmosphere, it's going to be supercritical fluid type thing, but here is a atmosphere where water could be in existence and dense enough to let some things swim around. Right, so looking at here, basically in this region that I've labeled with the red bar, the density ranges from 2 grams per milliliter down up to 6 grams per milliliter. So that's dense enough to swim around it. So that's kind of close to where the lower mantle densities on Earth happen to be. So that's pretty dense. There could be a lot of particles buoyant in the atmosphere, such a region, if we're in molecular territory. So that's kind of interesting place for chemistry to happen. So think of, if you're a science fiction writer, think of a gas giant that's got rings that are made of rock, and over millions of years, maybe these rocks are kind of raining down dust onto an area of your gas giant. Well, that gives you a lot of interesting chemistry that could happen that could support some life. Right. So the circle I've put on the Neptune diagram, that's kind of where I'm thinking of. There's another element here. Under these conditions, carbon tends to crystallize into diamond, and that would float, or not float, that would kind of precipitate out of this area and move down closer to the supraionic region or the rocky region. There might be some convection of all that stuff as well, because if you get too far down, those diamonds are going to redissolve. let's see, superionic water solid. Um, that the crystal structure I showed you that probably. Uh, honestly, I think the ionic water and superionic water would be more like the supercritical fluids. The crystal structures I show you are the solid forms of them, but under the pressures that we're talking about here, the water is going to behave very differently than it does. So, yeah, the ionic and the superionic basically have H pluses that are exceedingly mobile, OH minuses, or even oxygen dianides maybe that are exceedingly mobile. So yeah, this was saying that methane, CH4, in these regions might self-select to go away by waning out as diamonds. I'm conscious of my time here, so I'm going to go past that. So, um, yeah, so basically, paper from 2011, here's a quote. Our simulations also indicate that ionized water is, not surprisingly, an exceptionally aggressive chemical solvent capable of dissociating methane already at 50 gigapascals. So ripping the methane apart and making probably H plus and methyl anions and even further ripping apart. So that would be part of the self-selection for removing carbon. Because remember, if you're going to have silicon-based life, carbon can outcompete silicon chemically. So you have to kind of um, make this rig the system so that carbon has to lose, or so that carbon has to be selected out. And this might be an environment that could be realistic to make that happen. Right? Especially if silicon oxygen bonds, which are stronger, and silicon fluoride bonds, which are stronger, could persist. Right? This ends up being kind of our ceramic-based life, like the Horta. Maybe those things are Neptuna fish. Could be something that could um, come around. And again, it's going to be unlikely that the diamonds would persist as you go lower and lower. So there might be some carbon cycle sorts of things going on as diamonds form in the upper regions of this zone and rain down and then get um, um, destroyed and move back up. So yeah, so basically, maybe not Neptune, maybe not Uranus in our solar system, but we found all sorts of hot Neptunes and you know, all sorts of planets that are close to their stars, that are warm, um, that have atmospheric compositions. For example, this paper that I'm looking at here said they had found more carbon monoxide, less methane than they would have expected on the day side of the planet. Well, why not the night side? Well, I mean, they're looking at this with infrared, so you know, the hot day side is actually going to give a much stronger signal. But yeah, this thing of the self-selection of carbon to be, or especially methane, to be ripped apart under the conditions of these atmospheres will be, you know, something that would allow CO to be formed at the expense of CH4. Speculative, but I think it's something there. So here's some conclusions, and I'm actually finishing in time. So, you know, we might find Neptune-style exoplanets, especially hot Neptunes, to be interesting for writing about life. These ionic oceans might limit diamond faces, and maybe silicates could float as islands at higher latitudes, or if their life actually swim around at higher altitudes, I should say. But you know, you need, one of my points here is that you need to have strange conditions to get elemental abundances to the point where silicon-based life could compete with carbon-based life. And So here's basically my advice. Cryogenics, have things swimming around in ammonia oceans. Limit your water, limit your carbon. Um, you know, water is very soluble in ammonia, so you won't get regular ice if there is a little bit of water around. You can play with pressure to figure out your liquid phases. You could have a moon and one of these onion moons, or you could be looking at kind of a exo-Neptune or a planet like that. Um, but the biggest thing, if you're going to justify silicon-based life, you have to justify a weird fractionation of your elements. I like that diamonds are Neptune, a fish's best friend. So yeah, I'm going to stop there because these are older slides, and basically thank everyone for their attention, and basically, we'll go ahead and answer questions. I see one from Gus. Diamonds are forever. How could they redissolve? Yeah, some of our best friends betray us sometimes, and the diamonds, they think that they would last. But if you're going to have a aggressive solvent, that solvent can, like, the superionic water would pretty much pick off carbon atoms and redissolve the diamonds. Remember, if you heat a diamond up high enough in our atmosphere, it will burn. Right? They're not chemically inert.